In this video, we take a look at how you implement the Quicksort algorithm. So let's start again by checking what the exam board needs you to know for the Quicksort. You have to understand the main steps and the prerequisites of the algorithm, be able to apply it to a data set, identify the algorithm from its code, be able to read and trace the algorithm, and also you should be able to write the code for this algorithm. As its name suggests, the Quicksort orders a data set extremely quickly using divide and conquer. Divide and conquer means taking two or more identical smaller subproblems from a larger problem, solving the subproblems individually and combining their solutions to solve the original larger problem. The algorithm uses a pivot value from the data set, which other items are compared against to determine their position. A quicksort is often considered more efficient than a merge sort because it typically requires less memory, but this is not really the case. Whether one algorithm is better depends on several factors, such as the data set being sorted and the chosen pivot value. The Quicksort is suitable for any dataset but shines with larger ones. It's ideal for parallel processing environments where the concept of divide and conquer can be used. Typically found in real-time situations due to its efficiency, the Quicksort is often found in medical monitoring, life support systems, aircraft controls and defence systems. Here's an illustration to help you visualise a Quicksort. So here's the pseudocode for a Quicksort. As with the merge sort, you will notice there's a substantial amount of code here. To help you fully understand this algorithm, we're going to add an additional level of abstraction, step back from the pseudocode, and look at some simple structured English. So here's the pseudocode for a Quicksort, written using simple structured English. Now note that in step 2b, that could be a move to the left or a move to the right. The important part is that only one pointer moves. And we'll look at the different methods of implementing the Quicksort in the final thought section. Pause the video for a moment and just read through the steps of the simple structured English so you have a high level understanding before we proceed. We will now step through each stage of the simple structured English and explain what the associated pseudocode is doing. You will also notice that this implementation uses recursion. Step 3 and 4 both use a recursive call to the Quicksort function, and we'll look at that in more detail during the thorough walkthrough. So the Quicksort function starts when a list or an array is passed in. We're going to assume the list shown here has been passed in and the contents are of course unsorted. We then have a simple if statement that checks that the list contains more than one item. This line is a base case or terminating condition for the recursive function call. When the Quicksort function is called with a list containing only one item, it will start to unwind. Next, we set up two pointer variables, which will initially be set to the first and last item in the list. So pointer 1 equals 0, that's shown in red, and pointer 2 equals items.length minus 1, that's 4, and we're going to show that in blue. We now hit a while loop and check if we need to enter it. Pointer 1 does not equal pointer 2. Remember, with this algorithm, we're going to repeatedly compare the items currently being pointed to and swap them over if necessary. Once both pointers are equal, we'll know the item being pointed to is in the correct place, and this will tell us we're done with this branch of the algorithm and we don't need to enter the while loop. We then reach quite a meaty if statement, and we'll break that down fully when we step through some real Python code later. Effectively, this statement is asking, are the two items currently being pointed to in the wrong order? If they are, we swap the items and the pointers. This has been simplified down to a single swap line in the pseudocode shown here. At this stage, the algorithm would swap item 0 Florida with item 4 California, and it would also swap pointer 1 4 with pointer 2 0. We now move the first pointer one item towards the second pointer. Now, depending on the result of the previous if statement, the pointers may or may not be swapped. So before we move the first pointer towards the second, we need to check where it is. If pointer 1 is less than pointer 2, we're going to increment it to move it closer to pointer 2. If pointer 1 is the greater of the two, we're going to decrement it. Either way, we're moving it closer. Now remember, the while loop will execute until both pointers are the same. So let's take a quick look at how we'd get to that point. California and Alabama are in the wrong order, so swap items and pointers. Alabama and California are in the right order, so move pointer 1 towards pointer 2. Georgia and California are in the wrong order, so swap items and pointers. California and Georgia are in the right order, so move pointer 1 towards pointer 2. California and Delaware are in the right order, so move pointer 1 towards pointer 2. What we've effectively done with the first pass before we hit the recursive calls is work out where the pivot point is. We know several things now. California is in the correct place. Everything to the left of California is less than California, and everything to the right of California is greater than California. What we don't know at this point is whether these sublists are sorted and in order themselves. Indeed, we can see with the larger of the two sublists, although the items are all greater than California, they are not themselves in the correct order. The algorithm now repeats by recursively calling itself, passing in everything to the left of the pivot point, and then again passing in everything to the right. Eventually, once the recursive calls have all unwound, we will know that all the items in both the left and right sublists are in order. The final line of pseudocode joins or concatenates these three elements together and returns the complete sorted list back out of the Quicksort function. Here is some syntactically correct Python code that demonstrates the Quicksort algorithm in practice. We've added a hard-coded list of 5 American states stored in items, and we're going to pass this list into the Quicksort function. Let's trace it step by step as we have with the previous algorithms and see how it works. We will keep the simple structured English in the top right corner of the screen to help you follow where we are within the algorithm. The Quicksort function starts when a list or array is passed in and stored locally as items. We hit an if statement. If length of items is less than or equal to 1. Or length of items is equal to 5, 5 less than or equal to 1 is false. The condition's not been met, so we jump to the else part of the if statement. We now set up 2 pointer variables, which will initially be set to the first and last items in the list. We've color-coded these pointer variables so they'll be easy to keep track of as we work through the program. Pointer 1 will always be red and pointer 2 will always be blue. We now hit a while loop and check if we need to enter it. Pointer 1 not equal to pointer 2. Well, pointer 1 is 0, pointer 2 is 4, 0 not equal to 4 is true, so we enter the while loop. We then hit that meaty if statement, so let's break it down and help you understand it fully. We start by considering the two expressions in the first set of brackets joined with the AND. Item pointer 1 greater than item pointer 2. Well, item 0 is Florida, item 4 is California. Florida is greater than California is true. We then have pointer 1 is less than pointer 2. Well, pointer 1 equals 0, pointer 2 equals 4, 0 is less than 4 is true. The first set of brackets has now been reduced down to the Boolean expression true and true. We know that true and true equals true, so the entire first expression can simply be replaced with true. This value is ORed with the expression from the second set of brackets. Now, as anything ORed with true must be true, we can actually skip this part, but let's work it out this first time around. So we have items pointer 1 less than items pointer 2. Well, item 0 is Florida, item 4 is California, Florida is less than California is false. Pointer 1 greater than pointer 2. Well, pointer 1 is 0, pointer 2 is 4, 0 is greater than 4 is false. The second set of brackets is reduced to the Boolean expression false and false. And we know that false and false equals false. So the second expression can be replaced simply with false. By working through the expression step by step, we've reduced what originally looked like a complex condition down to true or false. We know that true or false with Boolean logic equals true. As the condition for the if statement is true, we enter the if statement. Now, we won't work through this if statement condition in so much detail in future passes. We know the items are out of order, so we need to swap them over in the items list, as well as swapping the pointers over. Now, in the pseudocode, we did this with a swap command, and depending on the data structure you're using to store the items and the language you're programming in, you might be able to swap the items over in a similar fashion. Here, we're going to use temporary variables to perform the swaps, and this is the same process we used when implementing the bubble sort. The actual swap is performed in Python as a three-stage process. We copy the value currently held in items pointer 1, Florida, and replace it into the temp variable. We replace the value of the item in items pointer 1 with the value of the item currently held in items pointer 2, that's California. And then we take the value stored in the temporary variable, which is Florida, and copy it over items pointer 2. We use a similar process to swap the values held in pointer 1 and pointer 2 variables. We check which part of the if-else statement we need to execute. So we check the condition pointer 1 less than pointer 2. So that's 4 is less than 0, which is false. As the condition returns false, we execute the else part of the statement. We decrement the value of pointer 1 from 4 to 3. We return to the while loop and check if we need to enter it again. Pointer 1 not equal to pointer 2. Well, 3 is not equal to 0, that's true. So we enter the while loop again. We check if we need to enter the if statement again. Now, we've laid out the logic there, but the conclusion is we end up with false or true equals true. The condition is met, so we do enter the if statement. Once again, inside the if statement, we use a couple of temporary variables to swap the items and their respective pointers over. We've simplified the animation this time just to illustrate the end result, but don't forget we'll be using the temporary variables. We now check which part of the if-else statement we have to execute. We check the condition pointer 1 is less than pointer 2, or 0 is less than 3 is true. As the condition returns true, we execute the first part of the if-else statement, and we increment the value of pointer 1 variable from 0 to 1. We return to the while loop, and we discover we need to enter it again. 1 not equal to 3 equals true. Again, we discover the items are currently being pointed to are out of order, so we swap the items and the pointers using our temporary variables. We now check which part of the if-else statement we need to execute. We've got 3 is less than 1 is false. So as it's false, we execute the else part and we decrement the value of the pointer 1 variable from 3 to 2. We return to the while loop. This time 2 is not equal to 1, so that's still true. So we enter the while loop again. This time, when we check the if statement, we discover that the items are not out of order. So we skip all of the swap code and move on. We now check which part of the if-else statement we have to execute. Pointer 1 less than pointer 2, or 2 is less than 1 is false. So we're going to execute the else section. So we decrement the value of the pointer 1 variable from 2 to 1. We return to the while loop. Pointer 1 not equal to pointer 2. Well, 1 is not equal to 1 is false. This time we discover we don't need to enter the while loop, so we skip past it. Now we've exited the while loop and the pointers are the same, we've found a pivot point for this initial set of items. This tells us that California is in the correct place. We now need to recursively call the function, passing in everything to the left of California, followed by everything to the right of California. If you remember back to our video on recursion, you will know there's a couple of things we have to do just before we call the quicksort function recursively. The system needs to push the return address onto the stack so we know which line of code to return to when the recursive function exits. We also need to push any data structures and variables onto a stack so we can get their values back when the recursive function returns. For simplicity, we're going to create a stack frame that contains all the information we need to get back when we return and push the entire frame onto a stack. How this happens behind the scenes is completely abstracted from you. The operating system takes care of it. What's important to remember is that we're about to execute a new recursive copy of the function with its own data structures and local variables. So we need some way to get back to the previous values when we finally return. Now we understand how to get back to this copy of the quicksort algorithm, we can proceed. So we start by recursively calling quicksort, passing in items 0, pointer 1. Well, pointer 1 is 1, so that passes in items 0, 1. Now this is a technique called slicing, which is available in Python. So items 0, 1 means from index 0 up to, but not including 1. In other words, it only passes in the item from index 0, Alabama. And that makes sense, as we're passing in everything to the left of our pivot point, which is California. The new recursive copy of the quicksort function starts when a list or array is passed in and stored locally as items. We hit the if statement. Now we've got this equates to 1 is less than or equal to 1, which is true. So we've recursively called the function, but the initial condition for the if statement has already been met, as the item passed in, or the items list, only contains one element. So this recursive copy of the algorithm immediately exits and returns items back out again. As the recursive copy of the algorithm returns, we pop the top item off the stack, which tells us what line of code to return to in the original copy of the algorithm, and restores the contents of data structures and variables that we previously stored away. The returned items list is assigned to left in the original copy of the algorithm. Now again, as we're about to make another recursive call, we push the return address onto the stack so we know which line of code to get back to, and push any data structures and variables onto the stack so we can get their values back. So here we are recursively calling quicksort again, this time passing in items pointer 1 plus 1 colon length of items. Well, pointer 1 is 1 plus 1 is 2 and the length of items is 5. So it's items 2 colon 5. Now in Python, that's slicing and it means from index 2 up to but not including 5. In other words, it passes in the items from indexes 2 through 4, which is Delaware, Georgia and Florida. And of course this makes sense because we're passing in everything to the right of our pivot point, which is California. The new recursive copy of the quicksort function starts when a list or array is passed in and stored locally as items. We hit an if statement. This works out to 3 is less than or equal to 1, which is false. The condition's not met, so we jump to the else part. We now set up 2 pointer variables which will initially be set to the first and the last items in the list. So they're set to 0 and 2. And again, we've shown those in red and blue. We check if we need to enter the while loop. Pointer 1 not equal to pointer 2. Well, 0 is not equal to 2, that's true, so we enter the while loop. We check the if statement and discover that the items are not out of order, so we can skip all the swap code and move on. We check which part of the if-else statement we have to execute. We see 0 is less than 2 is true. As the condition is true, we execute the first part and we increment pointer 1 from 0 to 1. We're moving the pointers closer together. We check if we need to enter the while loop. 1 not equal to 2 is true, so yes we do. We discover the items currently being pointed to are out of order, so we swap the items and the pointers using temporary variables. We check in which direction we need to move the pointer, and so pointer 1 goes from 2 to 1. We return to the while loop. This time we've got 1 is not equal to 1. Well, it's false. We discover we don't need to enter the while loop, so we're going to skip past it. So now we've exited the while loop and the pointers are the same. We've found a pivot point for this subset of items. And it tells us that within this subset, within this recursive call, Florida is in the correct place. We now need to recursively call the function again, passing in everything to the left of Florida and everything to the right of Florida. As we're about to make another recursive call, we once again push the return address onto the stack and any data structures or variables. Note how this stack frame is pushed on top of the stack above the previous stack frame, which is still present. So we recursively call quicksort, passing in items 0:1. This, as you know, means we're just passing in element 0, Delaware, everything to the left of our new pivot point, Florida. We know that once we're inside the recursive copy of the algorithm, the following actions are going to occur. The recursive copy will instantly hit a return statement as only one item has been passed in. So the top item of the stack will be popped off. The program will return to the previous version of the algorithm that called it, restoring its values, and the returned items list is assigned to left. So we're about to make another recursive call. So again, we push a stack frame onto the stack, including all the information we need so we can get back to it when we return. We recursively call quicksort, passing in items 2:3, which again, with slicing, means we're only passing in the item in element 2, Georgia, everything to the right of the pivot point, Florida. Once again, we know that once we're inside that recursive copy, it's going to instantly return if there's only one item being passed in. So the item will come off the stack, the program will return to the previous version of the algorithm that called it, restoring its values, and the returned item list is assigned to the variable right. So we've reached the return line of the original recursive copy. We return back out left, items pointer 1 and right, and these three elements are joined together or concatenated and return back out to the original version of the quicksort function. Once again, as the recursive copy of the algorithm returns, we pop the top item off the stack. The returned list is assigned to right in the original copy of the algorithm. Back in the original copy of the algorithm, all that is left to do is carry out the very final return. Once again, this joins together or concatenates the three elements and returns the sorted list back out of the Quicksort algorithm. Back in the main part of the program that we showed you earlier, we print the sorted list, which has been returned to the screen so the user can see the algorithm has worked. Of course, you can do whatever you like with the returned sorted list. For example, you might store it in another list or pass it into another part of the program. So let's consider a few final thoughts about the Quicksort algorithm. You might have spotted a slight inefficiency in how we've chosen to implement this algorithm. We didn't really need to recursively call the Quicksort algorithm when we only had a single element list. We could have chosen to put some simple checks around the recursive calls as shown here. For example, if the size of the list to be passed in is less than or equal to 1, we could store the list in left or right and skip the whole recursive call and returning back out. The algorithm still works as we've done it, but once again, this shows that one algorithm can have many implementations. As with many algorithms, there is often more than one approach that can be taken due to limitations for programming language, different programming paradigms, underlying data structures, or just different methods of optimization. The Quicksort is another algorithm where there are several similar approaches, and this can be confusing for students as marked schemes and other textbooks may present different answers to the same algorithm. Providing you show your working, the algorithm will still be recognizable and you will gain credit for an alternative approach. Having watched this video, you should be able to answer the following key questions. Can you successfully implement a Quicksort using a high-level programming language of your choice? And do you understand how a Quicksort works, and can you trace its code to explain it? We know that getting to grips with data structures and all the algorithms associated with them is a very tricky area of the course, and so we've produced a book called Essential Algorithms for A-Level Computer Science that's available on Amazon. It covers all the data structures you need to know about, along with the algorithms you need to perform on them, and it covers all the exam boards. We overview each data structure, discussing its typical applications and the operations you can perform on it. We provide a QR code that jumps off to a useful page of additional resources. We then take each data structure and the algorithms you need to perform and present them first in simple structured English, then in a diagrammatic format, then in pseudocode, and finally we present you with fully coded algorithms which you need to cover on the data structures in both Python and VB so you can actually code them up and practice them yourselves.